More specifically, how do bacteria grow? We'll focus mainly on those guys, right? So this is a picture I took in Yellowstone National Park. It's the only one where I could get like all the colors in one shot. If you ever get a chance to go, it's pretty awesome. It's like a drive-through safari. You'll actually get tired of seeing buffalo. I stopped taking pictures of them. The geologicals are pretty awesome. It is a volcano crater, right? So water goes through the different sections and are heated differently by the magma underneath. Old Faithful, the reason why the steam busts out on a pretty regular basis is the chamber. That chamber has not changed in a really long time. The architecture and stuff is still there, so that the water that gets trapped there gets heated up on a pretty regular basis and shoots out on pretty much a clock schedule. And that's why they call it Old Faithful. There are other sections where there's been shifts because of earthquakes, and it's no longer flowing. So Mammoth Falls, like that no longer looks like it used to. So it's constantly changing. It's dynamic. It's pretty impressive to a microbiologist like myself, because that beautiful color that you see there has to do with microbial growth. And it's microbial growth based on what parameter? What changes in that water? What physical attribute? The acidity level, yeah. But it's a volcano. Temperature. So you see the different colors? That's because it's the different temperature ranges within that pool. And so different organisms in that case are also different colored. And they're living in those different niches because of the different ranges of temperature that you see there. Mostly archaea there, because remember they like these extremes. But pretty impressive organisms. And this is actually where we found some of the organisms that we utilize in biotech industry today. They have enzymes that can be utilized and copy DNA at really high temperatures and stay stable. So polymerase chain reaction, right, PCR, wouldn't have existed without scientists discovering thermophiles, these organisms that can live in these really high temperature regions. So that's microbial growth at its best right there. Right, pretty too, right? So how do they grow? So they grow by a process known as binary fission. And this relates to their generation time, right? How often do they split? Do they double? And this depends on the organism, right? E. coli under ideal conditions, right? Best food, best temperature, great oxygenation, can double itself every 20 minutes. So if you start out with 1,000 E. coli, 20 minutes later you have what? 2,000, then 4,000, then 5,000. In your potato salad, the problem, by the way, is your onions. Onions are a rich source of sugar and a really good food source for microorganisms that may be present in your food. It's not really the mayonnaise in the potato salad that you leave out at room temperature, right, which is warm, which keeps bacteria happy and growing, right? Keeping them cold is better, but believe it or not, onions are one of your major problems with that. So binary fission, one cell into two cells, right? Not mitosis or meiosis, right? We don't have multiple linear chromosomes that we got to package up and make sure they divide equally. We just make a copy of the chromosome and we take the two pieces and bring them apart and separate all the stuff in between. It's not quite as complicated for bacteria. But as that time it takes to do that is going to vary. E. coli is super fast. Mycobacteria leprae, on the other hand, takes about a day, 24 hours to make a copy of itself. It's a very slow grower. Growth becomes exponential, though, right? Because we're doubling each time. 2, 4, 6, 8, 32, 64. That's about as high as I can go in my head. It gets big really fast, though, right? It's 2 to the exponential power. Growth in a petri dish is much different than growth in biological systems. Someone close the door for me, because I still have 10 more minutes, and I'm using them. Usually in a culture setting, we're dealing with one bacteria, right? Because, again, we're studying it. We want to know about that one bacteria. In natural systems, there are multiple bacteria growing together. And they create sometimes an architecture that we know is a biofilm. And this is an active area of research because it's a very serious problem for medical devices that are implanted into people. Okay? So I don't have any worries for my implant. It's just a little piece of titanium metal that apparently bacteria do not attach to. They don't recognize, my body doesn't recognize. I was like, okay, that's good news because you're not sticking something inside of me, right, that my body is going to form a biofilm on. Because bacteria, so people who get hip replacements, right, and knee replacements, anyone run into anybody where they've had it taken out and put a new one in, right? And the first time wasn't so great. Imagine having to go through it again. And this is because we have not been able to develop, although I don't know if maybe they can make titanium hips and knees and stuff, but bacteria can attach to these non-human surfaces. Okay, just like the slime that'll form in the bottom of your tub or your sink, that's a biofilm. How do you remove that? You got to scrub it, don't you? That's because those microorganisms have attached and they're growing together and they've created a matrix to keep themselves stuck there. So the bad news for us when this happens inside somebody's body is you're not going to go in there and scrub it off, are you? No. Because even when you do that in your tub and stuff like that, well, you know, it's going down the drain. You don't care about that. But reservoirs and stuff have become contaminated, right? And so imagine something being stuck in the bottom of your water supply, right? That's why they cover these things up now, right? Because stuff falling in could then attach and grow and little pieces break off and go into the water supply. So imagine inside your body, little pieces break off and travel to other places, cause infection in the heart or the lungs or brain, right? And antibiotics can't get at it, right? They can't get through those layers. Just like most of your cleaners, right? Scrubbing bubbles, yeah, it's great. But it's still not going to probably penetrate all the way through certain levels of biofilm or scum that can form in your bathtub or your sink. You got to scrub it, right? You got to physically remove it. We can't do that for people, right? We can't go in and scrub it. So instead, they go in and take it out and put something else in, a fresh one. So if you could engineer, right, a surface where biofilms don't attach to, everyone with hip and knee replacements would love you, and you'd probably be a gazillionaire, right? He's like, oh yeah, money, babe. But you see the need for it? But this is a natural thing, right? Microorganisms attach, they form these biofilms, these communities, right? It isn't just one bacteria. They're working in conjunction with each other. And that's the problem with treatment, right? We're not talking about just one bacteria. We're talking about potentially multiple species working in conjunction, and they've encapsulated themselves in a community. So if you have an antibiotic that you'd have to go layer by layer or section by, it's just not possible. It's just not possible. So as I said, the big scary thing with them is medical devices. They're forming on medical devices. Now, of course, microorganisms can be used for good. Right? Biofilms have been used in bioremediation and cleaning up problems. But they can create serious problems for treatment. So I'm trying to remember if I'll check after. So think about this too. So you need these things to grow, right? What chemical needs do you have in order to grow? What must you have? What do you need? Air, right? Whether it be the lack thereof or the need of oxygen or the lack of oxygen, because some microorganisms don't need it, right? What else? Water. Food, yeah. That one's kind of high on the list. So the major conditions that really affect growth, other than, of course, having food, are things like oxygen. Temperature, believe it or not, is extremely important for growth. pH. What is pH? Yeah, it's the partial pressure of hydrogen ions, right? How many free hydrogen ions are in a solution? This affects how chemical systems work, right? pH is very important. So we think of acids and bases, right? Does it give off hydrogen ions or does it absorb hydrogen ions? This will affect the chemical reactions within a cell. So you have to maintain a certain balanced pH level. Water availability. All organisms must have water to survive, right? Our pH balance, y'all, in our blood is extremely narrow range of you're still here and okay. 7.35 to 7.45. That's 0.1, a tenth of a pH. And you either convulse and no longer breathe and die, or you slip into a coma. Not good. Microorganisms are the same way. They have to maintain that balance. Temperature. Our reactions happen best at a certain temperature range, and then we said, remember, what's affected by temperature? Proteins. Proteins are the enzymes that catalyze your reaction, that create the structure in your cells. Same is true for bacteria. So if you heat them up, you destroy or permanently denature, destroy their proteins, you kill them. Same is true for us, right? There was a little kid the other day didn't want to go to school. His dad heard him taking his temperature, like the thermometers beep nowadays, right? Did he want to go back to school after break? He's like, well, at least he hasn't, my husband's like, he hasn't progressed to, the lighter. You can't do that with modern day thermometers anyways. But, if you had 109, right, you use the lighter too long, right? People don't go up to 109. You would be dead, right? 103, you better go to the emergency room, okay? So we have a set optimum range for us, right? 98.6. We want to kind of stay as close as we can to that. Because what happens to us if we get too hot? You destroy those proteins too, right? And your biological functions cease to exist. You die. So think about, right, as we talk about growth, these things that we know, how important temperature is, how important oxygen is, how important pH is, how important water is. Do we use this against microorganisms? Absolutely, right? We screw with temperature to kill them and preserve and slow them down. We limit oxygen availability. We change pH a lot, more than you realize, right? And we limit access to water as well. So we need these things to grow. We know how important they are to growth. We can use them to our benefit to stop growth. So growth and control kind of go hand in hand, right? So we'll kind of talk about both of them as we progress through. So we have 2 topics that are relatively short left for Thursday. Test is still Tuesday. All right, so I'm going to go quick. So So I highly suggest looking over this stuff. But the good news is, you guys know this stuff already, don't you? You know about growth and control. You do it every day, right? Every day. All right. See you guys Thursday.